Welcome back, students. Now let us go over to actual differential equation problems using the power series method. First, let us apply power series around so-called ordinary points. It's kind of difficult to define ordinary points, regular points, and singular points, and so on. So let's use some naive description here, not precise definition. Let's suppose we have a linear ordinary differential equation like this, and then if everything is continuous differentiable arbitrary many times, all okay, that kind of point is called ordinary. It is very naive description, but let's just accept that. And then around the ordinary points, we have analytic solution. And not only that, we have uniqueness as well. So no matter what you do, if you find a solution, that is the solution. Anyway, let us go through with an example problem. I think in this video, we'll have time for only one problem. And let's do this stupid problem. Why did I call this a stupid problem? Because this problem is a linear equation with constant coefficient. So you don't really need the power series method. You could use a Laplace transformation, or you could use anything else, and you're going to see much easier solution, sine and cosine as a matter of fact. But let's pretend you don't see it, and let's go with the power series solution. Okay, here we go. Let's take the power series, and let's go from there. Let's expand the font a little bit so that you can see individual terms a little bit easily. Let's see, original series like this, cn t to the nth power, okay. Take the derivative of each term, take one more derivative of each term, we get y prime and y double prime respectively. Our bread and butter. Next, let's apply index shifting, and that too should be your bread and butter. But this is for the first time, so let's go ahead. So y prime of t is this one, right? Okay, all right. All right, here let us apply index shifting. And basically what we want is we want t to the nth power there. That's what we want in the end. So how do you get n minus 1 into nth power? That's how. Let me expand the font still further. Our focus is upon this index here. This n I replaced into n plus 1, so that n plus 1 minus 1 total is just nth power. Maybe I should have highlighted this one. So what did I just do? N becoming n plus 1, so I have to do the same thing to all others as well. I guess that's it. Oops, I've lost n there. Okay, did I change all the n's into n plus 1? We have 1, 2, 3, 4 n expression. We have n plus 1, n plus 1, n plus 1, n plus n. Okay, all good. And let's simplify this as much as possible. Let's see. N plus 1 minus 1, so that's nth power. And then flip 1 to the other side, we get n going from 0 to infinity, and looks like that's the expression we have over here. All right, how about the other one? Let's begin with second derivative. And let's repeat the same expression. Again, I want nth power here. So how do you get nth power? N plus 2 minus 2, and that'll give me nth power up here. So I just replace this n by n plus 2. That means I have to do the same thing to everything here. So this 2 is n plus 2, that 2 is n plus 2, and this one n plus 2, and then that 2 is n plus 2. How's this computation? Okay, did I change all the n's? 1, 2, 3, 4, 5 n's into n plus 2, n plus 2, n plus 2, n plus 2, n plus 2. We got it. So that in the end we have t to the nth power. Okay, all right, we have it. Let's simplify this. And flipping this 2 to the other side, I get n running from 0, and n plus 2 minus 1, so n plus 1 here, and then nth power, and that's precisely what we have over here. So these two expressions, y prime and y double prime expression, were nothing more than just index shifting after taking the derivatives term by term. And this and that appear every single time. So you had better get used to these for all power series method. Not just for this problem, but all problems. Okay, all right, let's go back to the normal font. Can you still read it? I hope so. Okay, now let us apply this over here, and then this over there, and then we get, well, all right, here's the expression. Y double prime is this one here. I cannot read very well. A little bit bigger font, please. Okay, this y double prime is this one, as we have done over here. And then this one is just y, just straight ahead power series, no problem there. And then we take t to the nth power together. T to the nth power factored out. The sigma part is there, and what do we have here? Just a coefficient part. Now please note that the right hand side is constantly 0, so this whole thing has to be equal to 0 for every single t value, which means this entire function on the left hand side must be a 0 function. We cannot have any non-trivial coefficient. So this whole thing has to be always 0, and that gives me a recursive equation that I can solve c of n plus 2 with respect to cn. Excuse me, typo here. Sorry about that. Okay. Now that we have the recursive equation here, as a matter of fact, no, not really. Okay, that expression. So our solution is of this form, where c of n plus 2 is given by this recursive expression. This is what we got so far. Y of t is this power series, and with that difficulty we got this recursive relation. And from this point on, let's find out these values. What choice we have? Well, C0 is equal to, C0, n equals 0, plug in, n equals 1, plug in, n equals 3, plug in, and so on and so forth. Let's do it. From this expression, you plug in n equals to 0, then what do you get? C2 is equals to negative 1 over 0 plus 2, 0 plus 1, so we end up with this first line. Next, if n is 2, then this is 2 plus 2, so C4, and then this is 2 plus 2, 2 plus 1, and we get this expression. But then again, C of 2 come from the previous line, and then we get the rest of the line too. Please note that negative negative cancel each other out, and we have positive, and then we have factorial downstairs. Do it again, and we get negative and then 6 factorial, and so on and so forth. If you repeat it, and you're going to get this general expression. Please note that we have alternating sign, minus plus, minus plus, minus plus, and then the denominator is factorial with even number, 2 factorial, 4 factorial, 6 factorial, 8 factorial, and so on and so forth. Now that's because we started from C0, but if we start from C1, then n will have to be 1, that'll have to be 1, put it over here, and then we're going to get the first line. N is equal to 1, 1, so we get the first line. And then this is C3, so n has to be 3, so this is 3, 3. That's going to give me the second line. And what is C3? We can apply the first line, and then we get the rest of the second line. Again, please note, negative, negative canceled out, and then we have positive, and we have 5 factorial downstairs. Repeat it, we get negative 7 factorial, and so on. What do you have? We have alternating sign, again, minus plus, minus plus, minus plus, and then denominator is factorial with all those evens. So what do we have? We have solution. We have solution, power series solution with appropriate recursive relation, this and that generates this expression here. C. Oh, excuse me. Okay, there. And then this recursive relationship gave us this one for even and that one for odd. I think I made a sign mistake, which doesn't really matter because C0 and C1 really arbitrary constant, but let's make it right anyway. Yeah, that's right. We had minus plus minus plus minus previously, but here, according to this, we have plus minus plus minus plus minus. So it's better this way. Oh, no, excuse me. Previous expression was correct. Sorry about that. Previously, n was running from 2, 4, 6, and so on, and 1, 3, 5, and so on, but they both begin from 0, so no, this is correct. And do you recognize these functions? Sine and cosine. And then C0 and C1, those are arbitrary constants. So it doesn't matter whether you made sign mistake, plus or minus. It doesn't matter because they will absorb those plus minus anyway. As a matter of fact, I'm only half certain whether I did signs correctly here and there. Whether those minus or plus, I don't mind, because they're going to become right anyway in the end, because C0 and C1 are constants anyway. And that's how you can solve this equation using the power series method. That wasn't overkilling for a simple problem because this was a problem with constant coefficients, so you didn't really have to go through its power series at all. But we did it anyway, just to make sure that the power series method works. In the next video, we're going to do this problem, and this time the power series method will make a little bit more sense, even though the pattern formation for that recursive definition of those coefficients will be less spectacular and dirtier.